to 15. So when I come up with a spectrum and I say what depth was this, it says, well, it's 15 or 15 and a half or 16. So that's why you see this horizontal striping, but that's not a big deal. So that's one of the ways I can say how well I did. I also took all those plots or points and I plotted a histogram of the retrieved depths, which are labeled crystal here. That's the name of my software. And that stands for Comprehensive Reflectance Inversion based on spectrum matching and table lookup, I think it is. And then I was going to call it Multi-Environmental Techniques based on Hydrolite, METH. And so my software was going to be Crystal Meth. But then I thought, well, you know, the Navy's funding this, and that admiral says, you know, you're in the room at 8:30 and I don't like surprises, so I figured he might not see the humor in crystal meth. But anyway, so I just called it crystal. But anyway, the crystal retrievals are the database lookup retrieval. So here's just a distribution of points, and I really start at 2 meters because I didn't have acoustic depth much shallower than that, even though there's really a lot of pixels that were shallower. So here's just the distribution of retrieved versus actual measured. You know, once again, looks pretty good. The Navy has a criterion that says, I don't care how you do the retrieval, whether it's acoustics or optics or a guy out there with a weight on a string, you just guarantee me that your depths are good to 25%, and we're happy. So here I plotted the percentage differences retrieved minus acoustics over acoustics, and here's plus or minus 25% by the blue lines, and you can see that 95% of my retrieve points were within plus or minus 25% of correct, or 85% were within plus or minus 1 meter of the absolute depth. So that's how that all works out, and it can work very well. Assuming that your database is descriptive of the water that you're in, and assuming that your atmospheric correction is good. Here's just a map of bottom reflectance. So it's saying, oh, this area it's really bright. Yeah, that's correct. This area it's really dark. Yeah, that's correct. And then, of course, if you were flying, let's say, a 488 nanometer LiDAR, you would want to know what's the bottom reflectance. You don't care what's causing the reflectance, just how much will the bottom reflect light at 488. So that's what I plotted here. Or if you're interested in what's on the bottom, then you can go to the database and say what material was on the bottom, what mixture of things, and you can generate a map of the bottom type, where there's ooid sand, there's darker sediments here, there's sparse and dense vegetation, mixtures of coral, sediment, algae, and so forth. There's also a lot of speckle out here, little red and blue specks. And you think, well, that's probably not right. I mean, there's really not these little specks of coral there, and there's not little whatever. And what's going on there, if you actually go back at the image and pull out these funny-looking pixels, they're ones with white caps on them. So I'm just getting a completely bad retrieval. Well, why don't I remove the pixels that have white caps with some algorithm? And the reason is most of the algorithms for things like white cap removal, they look out in the near IR and they say, oh, it's bright out here at 800 nanometers, so that must be a white cap, so I'll throw that pixel out. Well, if you apply one of those algorithms to an image like that, you also knock out all your really shallow pixels because of their shallow water, so they also have a bright spectrum out at 800, but it's from bottom reflectance, not from a white cap. So I just left the white caps in, knowing that I'll get some bad retrievals, but I'll also get retrievals of the shallow waters here, which is maybe what I'm most interested in. And then there's also corals in here. There's a whole separate paper on how well did we retrieve the corals right here on Horseshoe Reef, and the answer is quite well. Okay. So another advantage of this thing is, this thing meaning the table lookup business, is that I can put error bars on my retrievals. And here's how it works. So the red curve is the image spectrum from this sensor called PHILS, which stands for Portable Hyperspectral Imager for Low Light Spectroscopy, developed by the Naval Research Lab, and that was Kurt Davis. And then sort of the grandson of PHILS is HICO, and now there's, other versions of it that the Navy's flying, but this was the first one. And so then I take the red spectrum here, I search through the database, I find the closest match, which is the blue curve here, and you can see it's quite a close match. But I show you in the green the next 29 closest matches. So here's 30 spectra that are extremely close to my image spectrum. And if I had had just like a little bit of different noise, on my image spectrum, I probably would have matched a different one of these green curves than the one I matched. So it's technically not non-uniqueness in the sense of the algorithm failing, but there's a lot of spectra in there that are very similar to the one I'm matching to. So I can't really be certain which one of these is really the best fit. Well, if I take these 30 spectra and I just say, look at the depths that correspond to each of those 30. Well, here's the distribution of that. Now, the closest fit here, the blue curve, the closest match said the depth was 11.4 meters. And that there's a tidal correction in there, so that's why it's a number like 0.37 instead of 0.25 or 0.5. So it says, closest match says it's 11 meters. If I just take all of these 30 and average them or take the median, I get about 12.3 meters. And the acoustic was actually 12.8 roughly. So by looking at a distribution point, or a distribution of retrieved depths, and then taking an average or a median, I actually get a better retrieval than if I just look at a single particular spectrum. So that's nice. And also, I can now say to the Navy, look, the depth here is somewhere around 12. It might be 11, it might be 13, but it's not 9, it's not 15. And that's often good enough for their needs. If they've got a boat with an 8-meter draft, I can say, go ahead and take it in here. If your boat has a 10-meter draft, maybe. If it's got an 11-meter draft, no, you don't want to go in there. So that's good enough for their purposes. And I can now generate a map where for each pixel I can say, here's my best guess at the depth, but here's some error bars, plus or minus a meter, let's say in this case. So it's often just as important to be able to put error bars on your retrieval as it is to get the retrieval itself. And you can do the same thing now for the bottom depth in the IOPs. Here is the closest matching one is actually underneath the red curve. In all these 30 retrievals, this bottom number 29 was retrieved 13 times, and that's also the one that was the closest match. And then there's some other bottoms here that were retrieved, maybe 1 or 2 times. Well, if you go back to the database and say, what kind of bottoms were all of these? The closest matching retrieval was 30% sand and 70% seagrass. These other spectra here are similar mixtures, maybe 60-40, maybe 80-20, but similar mixtures of sand and seagrass or sargassum, turf algae, or macrophytes. Now, if you're a biologist, you get all excited about the difference in seagrass and turf algae, but to an optics person, they're all just green stuff growing on the bottom. So optically, it's hard to tell the difference from one green thing versus another green thing, but I can be pretty confident that whatever it is, the bottom for this pixel is some mixture of dense vegetation, and it's probably seagrass, because seagrass was retrieved 13 out of the 30 times. Yeah.
In the lecture the other day, they showed those waves picking up a load of sand and things like that.
Yeah.
How much of an issue
Well, if you're in like the breakers there, yeah, this is going to fail completely. Yeah. I mean, at best, you'll be outside the database you've created for the clear water, so you're going to come up with some completely wrong retrieval. Or even if you had in your database spectra that correspond to this really high sediment water, you're going to retrieve that this is really high sediment water and I can't see the bottom at all. Yeah.
I know how you can do a statistical analysis of depth measurements, bottom depth, but how do you do the stats for nominal data just as like bottom type?
Well, unfortunately, I don't have, pixel by pixel bottom type data where I can say I got the right or wrong answer here, other than just kind of qualitatively saying, yeah, this is seagrass and that's coral over there. So all I'm doing here is saying all of my pixels retrieved some kind of green bottom, seagrass, sargassum, whatever. So it was a green it was a green bottom at this roughly 12 meters depth, and it's mostly the vegetation with maybe a mixture of 20 or 30% sand in there. And so I really can't say anything more than that. And like I say, I would love to go back and go to this point and see what's actually on the bottom. And the guys in Australia, Arnold Deckert, Stuart Finn and company, they have done this kind of stuff now for 8 or 10 years, and they've got, with similar kinds of algorithms, they're spectrum matching algorithms, they have done a very good job of being able to say what species or what type of coral or seagrass or whatever it is. So they're definitely the gurus of this field. And the reason that Australia has spent so much money on this is that there are something like 60% of Australian waters are still using charts made by Captain Cook in the late 1700s. And so they want to have something slightly better than that. And I guess now maybe they've got aerial, charts, bathymetry charts generated from aerial things that have now pretty well covered all the Great Barrier Reef and so forth. But basically it was, 200-year-old charts that they were using for a large part of Australian waters. Well, enough said. You can do the same sort of thing for the IOPs retrieved from that pixel. All 30 of the IOP retrievals basically said this is the absorption spectrum. They're less certain about the scattering, and they're very uncertain about the backscattering. And all that's going on there is for the light to get from the surface down to the bottom in, this was about 12 meters of water, and back up, absorption is really what determines how much of that light gets to the bottom and back up. And this water is so clear and shallow that the backscattering by the water column is less important than the bottom reflectance. So it's just kind of throwing all of its ignorance into the backscatter and saying, I don't know what the backscatter is to better than a factor of 2, and it really doesn't matter too much anyway because it's the bottom reflectance that's determining my signal. Okay, so that just says what I just said. So here's just a couple of examples now of how people use this on a daily basis. In the U.S., kelp is a big deal. It gets used in your ice cream and in medicines, and it shelters fish, and scuba divers like to go out and get hung up in it. And so it's very strictly managed and very strict rules about how to harvest kelp. Now, it's like the world's easiest remote sensing problem because you have this reddish brown kelp against blue or green water. So it really shows up well in an image, and there's no doubt that it's there or not. And so here's some imagery from an airborne sensor called Samson. This is California, so this is coast of California. This is, a couple of kilometers here as I recall. And here's a 2002 map of the kelp coverage binned by 10% in drawing this map. If I take a little area of water here, that's sort of like 100% kelp, and then the white is 0% coverage. So here's a kelp map of a section of the coastline, 2002, same coastline 2004. Question, where did all the kelp go in 2 years? Answer, I don't know, not my problem. I only do the imagery. You're the ecosystem manager. I mean, did global warming kill it? Did fishermen cut it all up? Did it die of old age? I don't know. That's their problem. But you can see this is why people are interested in being able to run out there and get meter scale imagery for purposes of ecosystem management. It's the only way you can do it. And if this were, you know, a CWIFS or a MODIS pixel, it would be like this big and you couldn't tell anything. Okay, here's another study from a master's thesis. Here's open ocean. Here's a barrier sand beach area here. And then here's a little inland bay, which pretty much drains at low tide, and then high tide, it's a meter or two deep. But doing this thing and looking at what comes back, these light green lines are eelgrass that tends to grow along the sides of these deeper channels where the water drains out as the tide goes out. And apparently nobody had any idea this stuff was growing there until it just shows up very nicely in a hyperspectral image like this, where in the database you have eelgrass and mud and all these other things, and lo and behold, it retrieves all this eelgrass, and people say, well, that's interesting, let's go out there, and yeah, sure enough, it's there. So that was her master's thesis. One final view graph on the non-uniqueness business. When I started on this 15 years ago or whenever it was, and the Navy said, you should look into this, I said, I guarantee you it won't work, because how are you going to tell the difference in high chlorophyll green water and deep water with high chlorophyll concentration? You get a green spectrum. If you have clear water with a seagrass bottom, you get a green spectrum. You can't tell the difference. And here's two examples here where I'm plotting the normalized remote sensing reflectance. The red is infinitely deep water, chlorophyll of 10. The blue is 2 meters deep water, fairly clear water, and a seagrass bottom. They're both pretty much the same shape. And now I'm going to come along with an image spectrum that looks like that. I'll never be able to tell the difference. Well, when I actually started doing this, it works just fine, and there's no non-uniqueness problems. And then I realized, well, they are non-unique for the shape, but when you account for the magnitude, they're much different spectra. So here is now, in calibrated units, remote sensing reflectance for the high chlorophyll water, and here's the remote sensing reflectance for the shallow bottom. Sorry, did I get that right? Yeah, right. Okay, so let me think. Blue is, sorry. Yeah, no, I said it right. So there's my seagrass bottom, and there's my deep water with chlorophyll. They're a factor of 2 or more different in magnitude. And the reason is, you know, one of them has this dark bottom and the other one has lots of particles in the water that cause scattering, but it's got a lot of chlorophyll that it causes more absorption, etc. So even though they're both green spectra, the magnitudes are different. So when I come along with a spectrum like this or a spectrum like this, there's no problem telling the difference in those two. So the whole non-uniqueness problem just wasn't there. When you have radiometrically well-calibrated spectra and good atmospheric correction, there was never been a non-uniqueness problem. And when I do these retrievals, like the ones there in the Bahamas, in my database, I also had things like kelp spectra, and I had infinitely deep water to see if I would occasionally retrieve those. And in those images, never once did I retrieve a kelp spectrum in the Bahamas. Never on one pixel did I retrieve infinitely deep water or even 30-meter deep water. So there was just no non-uniqueness there of mixing things up. So that's the story on airborne remote sensing. The Chinese are huge on this. They have, you know, a couple of aircraft that are just sitting there with hyperspectral sensors. And if you're a Chinese scientist, you just call them up and say, hey, I'm doing this experiment out in the South China Sea or the Bohai, which is sort of the Yellow Sea, part of the Yellow Sea. I'm doing this oceanography experiment. Would you come up and fly over and get some imagery for me? And, you know, it just takes a phone call. The Australians are big on it. The people around the Baltic, so Tiit Kutzer in Estonia and people in Sweden, Susan Kratzer and so forth, they do a lot of this stuff, remote sensing in the Balkans, or in the Baltic waters, because there's a lot of harmful algal blooms there and so forth that they're interested in. So they're a big group doing this. The U.S., you know, the NASA program now is going to be a big program doing it. And that's my story. So it is important. It's just not the sort of traditional ocean color remote sensing from satellites, but it's still there and it's still important. So that's my closing picture here. You know, basically I use sea kayaking as an excuse to go to exotic places and see what's going on. And my wife and I just kind of throw darts at the board and at the map, and it hits Fiji one year and it hits Greece the next year, and then we say, well, you know, we should go check that place out, see what's happening over there. So I like doing that, and you meet a lot of colorful people, of course, in all these different countries. And if you go to India, which I haven't been to, but this guy was in Nepal, he's a sadhu, which is basically means holy man. And the sadhus have renounced all earthly pleasures, all family ties. They have no material possessions or anything. Their whole goal is to spend the last few years of their life meditating and practicing yoga in the hopes that they will achieve moksha, which is freedom from the endless cycle of birth, death, and reincarnation. And so they're Hindus. So if you want to become a sadhu, it's pretty complicated business. You can't just walk in the door and say, here I am. You have to go through all this apprenticeship and so forth, and you know, have a guru and be a slave to this guy for 20 years. And then you finally get to be a sadhu. And part of that is you attend your own funeral. And in India, sadhus are considered legally dead. So this guy is nothing at all. He is a dead person just walking around. And you're supported by the local villagers or townspeople. You sort of show up at their door and they give you a meal and then you move on. And some of these guys go up in the Himalayas and live in caves, and some of them hang out in Kathmandu and make money off of tourists taking their pictures. But anyway, that's the story on one of the guys I bumped into at a temple, Hindu temple in Kathmandu, and they have the most amazing, you know, I don't know what you would call it, symbolic body painting there. And I guess if you get good at it, you can tell which little sect of Hinduism they belong to by how they paint themselves up. And some of them are sitting there, you know, you'll be walking down the trail in Nepal on your trek, and this guy will come along buck naked because he's got his sky clothes on, which means no clothes at all, because he's totally renounced even clothing as any kind of connection to this world. And so you give the guy a quarter or something and send him on his way. So that's the story. That's Namaste in the Devanagari script that's used to write Hindi and Nepali and so forth. It means namas means like a reverential bow, and te is used. So namaste is the standard greeting coming and going in Nepal. You walk down the trail, everybody you see, it's namaste, namaste, which means basically something like I bow to the divine in you. But here, you know, you do something and somebody says, oh, God bless you, young man. You kind of feel like they don't really mean it. It's like drop dead, you know, get out of my way. But there, you kind of feel like it's such a spiritual kind of place where religion is just a part of society, that when you see people on the trail and you say namaste, you know, they really mean it. So it's a very interesting experience. And I highly recommend you go hang out in these places for a while and get a different view of the world. And so Actually, in Nepal, what you'll say when you're on your trek is you say namaste, and then you ask about the trail. And is the trail Ukalobato or Uralobato? Is the trail steep uphill to where I'm going or steep downhill? And as far as I can tell, in Nepali, there's no word for level trail. You're always going Ukalobato or Uralobato, no level trails. So that's it. End of my talk. You have now survived all of the lectures, and namaste.